computation using CUDA. The problem at hand is that let's say for example, we have a list of alphabets or just any other sentence. We have like, I am a good boy, something like this. And we need to plot the frequency of every letter. So A, B, C, D up to Z. And let's say this is an entire document. And in the document, we need to find the frequency. So, for example, A occurs 10 times, B occurs 20 times, C occurs 5 times, and so on. Z occurs 1 time. So, we need to plot this histogram of frequencies. The easy way in serial programming would be something like this simple C function, where we iterate over the length of the document. For every alphabet in the document, we calculate the position of the alphabet, and let's say we, instead of calculating the frequency for each alphabet separately, like A, B, C separately, let's say we um, want to uh, like discretize it into 4 buckets, and the first bucket is responsible for calculating from A to, let's say, I, from J to, like, I mean from 0 to 9, 10 to uh, or 26 by 4 is what is it, 26 by 4, uh, 6, right? So first 6 characters come here, next 6 characters come here, next 6 characters come here, and last 8 characters come here. So A, B, C, D, E, F come here, and the next come here, 6 come here, next 6 come here, 8 come here. So this is a simple C loop implementing this. If you want to do the same thing in CUDA using parallel programming, we would do something like entire document. Let's say this is the entire document. We assign each thread, like this is the first thread, second thread. We assign each thread to each data point. So if we have n data points, we assign each thread to n data points. Each thread calculates the alphabet position, and each thread updates the histogram alphabet position by 4, by like increments it by 1. But the problem is that it might be the case that all the three um, threads 1 to 3 have A in them. So since they are occurring in parallel, these threads are executing in parallel. When they try to execute this statement, we can have a data hazard. By data hazard, I mean uh, like, since this statement might be being executed by 3 threads, like 3 threads are accessing the same memory location concurrently, we would expect that if initially memory location this memory location had value 0, after these 3 updates it should have a value 3, but because of a data hazard it might have a value 1 or 2 or 0 or 3, any of them, and this is not what we want. And the reason for these data hazards is something called race condition, where um, let's say for example, like each increment can be broken down, each value plus plus operation can be broken down into 3 atomic operations, and if the order is not like sequential, that is if all 3 operations of the first um, thread do not occur before all 3 operations of the second step, that is like if there is some interleaving of operations, like in this case, then we might have a data hazard where instead of value going from 0 3 to 3, it might go from 0 to 1 or 0 to 2 or 0 to 3. We do not know this. So the way to avoid this is by using something called atomic add. So CUDA guarantees that if we use atomic add on a given variable, all the three atomic like if this is the variable plus plus, if we use atomic add on variable, we discussed that variable plus plus can be written as three atomic operations, right? So if we use atomic add on variable, then all three operations will be executed together. There will be no interleaving of another thread's atomic add. This way we can guarantee that always variable uh, plus plus executed by three threads would result in 0 to 3 instead of 0 to 1 or 0 to 2. Okay, now the CUDA kernel using atomic add is simple. Just we use atomic add, and the rest is very close, very similar to a serial uh, in the serial code, where like every thread calculates the position it has to operate on, calculates the data, the alphabet position, and does an atomic add on it. But the problem with this is, let's say all of the positions, all the document, like all the positions in the document had A. So all threads would execute atomic add on uh, the bin number 0, like 0 A, B, C, D, E, F. On this bin, they would execute atomic add. But uh, recall that the memory access latency for global memory is very high. And typically, we hide that memory latency by executing multiple operations in parallel. But in this case, since each thread is executing atomic add, and CUDA guarantees that atomic add will uh, result in a serialization of these in threads atomic add operation. So we would basically have memory access by thread 1 followed by memory access by thread, let's say 3, by followed by memory access by 5, followed by memory access by 2, followed by this. So each memory access has a latency of the actual global memory access latency. So there is no latency hiding here. And because of this, the uh, execution time of the kernel would be too high. So we would want to optimize that now. And the way we optimize this, yeah, so this is what is discussed here. So the way we optimize this is using something called privatization, where instead of the uh, entire document having one histogram, we break down the entire document into chunks, let's say 4 chunks, and each chunk has its own histogram, each chunk computes its own histogram in step 1, and in step 2 the 4 histograms are merged into just one histogram. That is our answer. Now the plus point of this is that in each chunk, the data contention, that is the number of threads that would potentially be operating on the same memory location, that is lesser than the last case we discussed. And the downside is there is an extra merging step in this privatization method. So we discussed like how this is implemented, and in implementation, each block, we said that the document is broken down into chunks, right? So in our implementation, we define each chunk as one block of the grid, and each thread block has its own histogram. So contention between threads, contention inside in this implementation is only between threads inside a thread block, because threads within a thread block share the same histogram. So the code here, first part of the code, this is like each thread is trying to fill the its own histogram, and then this is the first part of the algorithm, and this is the second part of the algorithm where we merge histograms. And the way we describe so we said that each thread block has its own version of histogram, right? So we describe histo as if there are x blocks, we have x histograms, and each histogram has n bins. So in total, there are like n into x elements in the global memory. Instead of initially, like previously, we had just n elements in the global memory, right? Because the histogram was had n bins. Now we have n times x bins. Um, yeah, so in the first step, this entire histo array of size nx is populated, and in the second step, we make sure that all of the thread blocks which are greater than index 0, that is h2 to hx, threads in these thread blocks give their contribution to the first histogram in the merge step. So for example, if n, that is the number of bins, is 10 and the block dimension is 30, so in each block, the first 10 threads of each block add their contribution, that is, add the histogram value corresponding to that thread to the histogram value corresponding to that thread in histogram 1. Okay, and in if n is equal to, if there are like 90 bins and the block dimension is 30, then each thread um, adds three elements, adds the contribution of three elements to h1. So this is similar to like thread coarsening, where each thread does three times the computation. Eh, yeah, yeah, yeah. Okay, so and now an observation with this approach is that uh, since each block had its own histogram, why not, like, we always think that if there's a structure that is mapped to a thread block, then what is one memory in GPUs that follows this pattern? That is shared memory, right? So instead of loading the histogram of each block into global memory, like instead of defining histogram of each block into the global memory, we describe histogram of each block into the shared memory. If like this, obviously, if there is enough shared memory for this. So first we initialize the shared memory per block in this step, like 4 to 6. Then in 8, 9 to 15, we uh, populate the, like, the do the atomic operation, do this very similar sort of computation as we did earlier, like in the last implementation, with global memory, each thread block having its own histogram in global memory. Uh, just now we have shared memory instead of global memory. And note that atomic add in the shared memory would be much faster than atomic add on the global memory, because latency of shared memory is much less than latency of global memory. So once this step is done, we do a merge step where instead of reading from the global memory, we read just from the shared memory. Okay. Now another optimization that can be done on top of this is okay. So we see that in the merging step, or even like in the when we are defining the um, atomic adds, right? If when we are defining the histogram of each block separately, what if if the number of blocks is less than the number of SMs? What I mean by this is, if all the blocks can execute in parallel, then this is okay, because since all the blocks are executing in parallel, there's not much latency, there's not much waiting we have to do. But on the other hand, if let's say the number of blocks is five times the number of hardware resources required to uh, execute all the blocks, yeah, yeah. So if the number of blocks is five times the number of SMs, then we have to, then the hardware essentially sequentializes all of these five um, five implementations into five iterations. So we do not get a benefit by uh, by using GPUs, right? Because we are okay. So whenever we use GPUs, there's a cost of parallelization, where we have to launch thread blocks and like do the computation in parallel. So this cost of parallelization is generally overshadowed by the parallel execution. So if the number of blocks in shared memory could fit in the shared memory, could fit in the I mean could be executed at once, then it would have been worth it. But if the number of blocks is five times, like do we have to do this computation in five steps. Why not just launch? Why not just? I mean, why not just assign five times the computation to each thread, right? And so that we can avoid the cost of parallelization, and we can also still do all the computation. So this is called as thread coarsening. We followed we could follow two strategies where one is continuous partitioning and the other is interleave partitioning. In the continuous partitioning scheme, each thread covers is responsible for covering continuous elements, data elements, and in the interleaved partitioning, like a series of threads, all of the threads and the threads operate on consecutive data elements, but the same thread operates on uh, different, like how do I put it, like in 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 continuous partitioning, the same thread operates on continuous data points, whereas in interleave partitioning, the same block, threads within a block, operate on continuous data points. And you can see that the memory access pattern in case of continuous partitioning is not optimal, because in a warp, threads operate on this, like all of these data points, and these are not continuous. So the memory access pattern is not coalesced, whereas the a warp threads in a warp operate on this and so on data points, which leads to a coalesced memory access pattern. Okay, so using interleave pattern, each thread does coalescing in this way, and in um, yeah, and in continuous partitioning, each thread does partitioning in this way. Okay, yeah, so this is our discussion of histogram um, computation using parallelization in GPUs in CUDA.